So let's start with a quick screen share. Our goal is to get through chapter 33, and then at the end of class, we can talk about quiz questions if there is one. This simulation is the best one I could find for right now. So I don't know if you can see this thing, but on my screen, I have some red and blue waves oscillating. Now, this one is not set up the same as our picture, but if I could bring your attention to right here, and I know that for colorblind, this may not be the best, but notice if you look inside of there, there's an electric field that's oscillating up and down. So there's an electric field. And actually, let me get the eraser to get this thing out of here. And then there's also a magnetic field that's oscillating kind of in and out this way. So we see there's two different sine waves. And I want to point out something that's weird about this compared to just an oscillation. If you have something that oscillates, it goes back and forth, but on average, it stays in the same place. A wave differs from an oscillation in this key respect. In a wave, energy is transmitted from one location to another. In an oscillation, the energy on average stays in the same spot, right? It's right where the oscillation is happening. Now, what's complicated about this that you might not understand, where does this wave come from? I don't know if you can recall, but last time I showed an electron and we showed that an electron could be wiggling up and down. Now, I think you could agree if you had an electron wiggling up and down, it might make sense that the electric field would wiggle up and down, just like in this photo here or this animation. So the electric field is going to wiggle in the same plane as the electron, or, you know, you could in theory do it with a plus charge too, but normally you do it with an electron and an antenna. So the electric field is going to wiggle up and down because we have a charge that's wiggling up and down. The magnetic field is perpendicular to that. So we have this magnetic field here. All right. And if you don't recall, the idea here was this very unusual thing happens where if we just purely looked at chapter 21 and 22, where we talked about the static electric field, the electric field associated with any one position of the electron, these waves would not travel. However, from Maxwell's equations, we discovered, oh my gosh, a changing electric field can create a magnetic field. Likewise, a changing magnetic field can create a, what did I say? A changing magnetic field can create an electric field. So if you think about this electron moving up and down over here, right? That's both a current and a wiggling charge. So you've got a changing current as this electron wiggles, right? So that's a changing B field. And then you've got the changing electric field from the location of the electron. So that's what gives rise to these propagating waves. We say it propagates because it brings energy from one spot to another, say from the sun to your face. Okay. So let's go over, and while that animation is cool, let's look at some words. Okay, so this is page 225. So this is my attempt to simulate that. And notice right here, this is a snapshot at one instant in time. Now notice I've got a slightly different set of coordinate axes than that demonstration I had, whatever that thing is. Let's get that out of here. So in this case, these black arrows are in the XY plane, and that's the electric field. And then I don't know if I have gray here, so I'll kind of use this green color. Well, I'll use blue. This is the B field here, the dotted gray arrows. Okay, so those gray arrows are supposed to be the B field. Now, again, they're in the XZ plane versus the black arrows in the XY plane. Okay. Now, what's very special about this is these electromagnetic waves can travel through space, emptiness. We do not require a medium. Now, what do I mean by that? Water waves travel through water. String waves travel through string. Earthquakes travel through earth. So all these different sound waves travel through air. So all of those different types of waves require a medium to travel. They require some stuff for the energy to be transmitted. Electromagnetic waves are so special, they do not require this. It's just amazing, right? It's literally the change in the electric field and the change in the magnetic field that causes this to work. Notice this cool trick. If you want to know which way the energy travels, E goes to B goes to way energy travels. So on this picture, which way is this wave traveling? Is it traveling in the I hat, J hat, K hat, where? Negative, plus?
Positive I hat.
Yeah, so line up your fingers with E, curl them to B, and my thumb points to the right along the X. So this is actually a wave that's traveling this way. So that's the velocity of the wave traveling this way. If it's electromagnetic, it's probably C, but if it's going through glass, it might not be C. So, but yeah, remember this. E goes to B goes to way the energy travels or way the wave travels. E goes to B, shows you the direction the wave travels. Okay. Now, there are a lot of words on here. So let's see if we can pick our way through this. And let's just start with these ones. Okay. K is a new thing. It's not a spring constant anymore. It's not a Coulomb constant. It's not some other constant. This K is called the wave number. Now check the units. Notice the units are meters to the -1. So if you see a symbol that says K and its units are meters to the -1, that tells you it's a wave number. Wave numbers are very handy in certain cases. This relationship right here, you had better have this memorized if you're in this class by now. This is something that shows up all the time. You know that period, frequency, and angular frequency are all related. Now check this one out here. And I want you to compare this to up here. The electric field is oscillating in the J hat. So notice this sine function here is going to be positive and negative in the J hat. That's why these arrows are up and down on the J hat axes. All right, there's the Y axis. Sorry, it's a little cut off. Now, on the other hand, I'll do this one in blue. This one is going to oscillate about the K hat axis. So notice it's plus on this side, it's minus on that side. So the B field is oscillating in the K hat. So notice these, this symbol right here and this symbol right here tell you which direction this thing is oscillating. So the magnetic field oscillates in the parallel to the y-axis, and similarly, the electric field oscillates parallel to the J hat axis. Now remember what we said. This thing is traveling in the plus I hat direction, right? Now I'm going to have to sneeze pretty soon. I can tell. So if I suddenly just mute, it's because I'm about to sneeze. Look at this kx minus omega t. That is the piece that tells you this. If you see a wave that's propagating in the I hat, you would expect kx minus omega t. If it was, if we used kx plus omega t, it would be in the negative I hat direction. So that's what I wanted to get here. Maybe write this down. This kx minus omega t means you're traveling in the positive I hat. Kx plus omega t means you're traveling in the negative I hat. That's what I was trying to mean by this comment. Okay. And then a couple of other things. You're kind of getting used to this. This is an amplitude. So this is the electric field amplitude, B max. And so that's just the largest value right there, right there. And then this would be the largest value of the B field. So again, the amplitude is simply the peak size. So that would be the maximum amount of magnetic field in the wave. I'm going to pause for a second. Any questions? Okay. Some of you that have had 162, this should all be review. Remember, some students have never seen this before, so be a little patient, okay? Next, wave speed. Wave speed, this is a big deal. Everybody better remember this equation for the rest of your frickin' life, okay? Wave speed equals frequency times wavelength. Now, what is the wavelength? You can see it right here. Notice in this case, this is x. That means this distance that I'm outlining on this picture up here is a length of a wave. So this is now a wavelength, not a period of the wave. Because this picture is showing all spatial dimensions, x, y, and z, we're talking about wavelengths when I look at this picture, not periods. When we did our lab last week, there was all these waves on the screen, and the x-axis was time, and the vertical axis was voltage. So there, when we went from crest to crest, that was a period. Well, this is no longer the case for these electromagnetic waves because we're looking at the wavelength instead of the period. So always, always, always double check the axis labels right here to see if you're talking about a wavelength or a period on the horizontal axis. Okay. Okay. Enough said on that. In this one down here, c is the speed of light in a vacuum. Okay. All right. So just remember that has to be in a vacuum. You're going to handle non-vacuum situations in Physics 162. But for this class, we will only have light waves in a vacuum. We're not going to deal with polarization, etc. So it's going to be really simple. We're going to talk about light waves traveling in a vacuum. All right. So let's keep going. Now, sometimes maybe you've heard the corpuscular nature of light. Light can be treated as a particle or as a wave. So sometimes when we're talking about the wave properties, we're going to use all of these things. We talk about its frequency, its wavelength, its sine function, etc. However, we could also talk about it as a particle. If we think of light as a particle, sometimes this is written E gamma, meaning gamma is the symbol for a photon. And that's noted right here, E gamma. But H is just some number. It's Planck's constant. You are going to learn all about it in Physics 162. Notice there's different units. If you're dealing with EVs versus joules, the units change the number. But a very convenient number that you can use for test questions is this. HC is 1240 EV nanometers. Why is this useful? Energies for single photons are usually written in EVs, and wavelengths are usually written in nanometers. So as a result, if you know E or lambda, knowing this number makes it really easy to get the other one. So no tricks there. It's just a convenient, it's basically the most common units for energy and wavelength of photons are EV and nanometers. Nothing special. So before we scroll down, any questions about this? It's just basically some BS equations you need to know how to use. And we're going to practice them in a minute. All right. Okay, so let's scroll down to right here. This one, we actually did this earlier in the semester. Remember the velocity selector problem and the crossed fields? It turns out this is still true. The speed of a wave is related to the Emax and the Bmax. Now, something I want to point out here. This is a little bit weird. I just want to point out that Bmax equals Emax over C if I rearrange these, right? And C is something like 3 times 10 to the 8th meters per second. It's a very big number. So if you look at these numbers, basically the magnetic field amplitude remember this, give me a second. This is the electric field amplitude, the size of the largest electric field in the wave. Over here is the magnetic field amplitude, the largest magnetic field in the wave. If we look at these, what do you notice about the size of B max compared to the size of E max?
Much larger.
Yeah, B max would be 1 billion times smaller, right? Because it's divided by 10 to the 8th, which is almost 1 billion. However, when you look at the energy, it turns out the energy, which relates to this equation right here, I just want to point out, it turns out the energy is equally split between the electric fields and the magnetic fields. So it turns out a very tiny magnetic field can have a lot of energy in it. In fact, the same amount of energy as the electric field. So that's all I wanted to point out. You might think that most of the energy in an electromagnetic wave comes from the electric field because its number looks so much bigger. That's not true. The energy is split equally between the electric fields and the magnetic fields as it travels. That was just a fact I wanted to express. Nothing special there. All right. This one is called the pointing vector. Now, a funny little misnomer here. The pointing vector points in the direction the wave travels, even though it's named after somebody that just happened to have a name Pointing. So this is very cool. It turns out this name happens to match the description for once. This right here is called the pointing vector. And notice E goes to B, goes to the direction the wave travels. So S, or the pointing vector, represents the direction the wave travels. Now, if you're a big beer drinker, you might recognize this as an IPA. The IPA is intensity is power over area. Now, give me a reminder. What are the units of this? What are the units of power?
Watts.
What? What? Okay, very good. Doesn't quite work the same over ERT. All right, and area is meters squared. So notice intensity relates to this pointing vector. So that's what this thing is actually representing. It's how intense the wave is, or how much power is being delivered per unit area. So obviously, if you shine a laser beam on your eye, it's a lot more intense than if you shine a flashlight on your eye. If you shine the laser beam on your eye, you might be blind for the rest of your life. If you shine a light bulb, a flashlight in your eye, you might be blind for a few seconds, right? And so clearly there's a difference in intensity. Intensity is this pointing vector. On average, the average intensity gets this factor of 2. Do you see that? So that comes from the average of a sine wave. If I could, oh, shoot, wrong button. Sorry about that. Whoops. If you average these sine waves, you get this half. So that's where these formulas come from. That's the average intensity. Next. Okay, power over area. We'll get into some problems. Now, this is something weird. When you shine light on something, you can actually exert a force on it. So right now, I am actually inflicting a force on your face through the photons coming off your screen. As obnoxious as that is, now, obviously, this is imperceptible to us because it's a very small force. However, we will talk about an unusual example where that force is noticeable. All right, so we'll do that in just a second. Or like half hour. Come on, screen. Any day, Zoom. There we go. All right, so something you got to watch out for here. Everybody, stay alert here. Watch out for this one. Notice there's power, and there's pressure, and then there's momentum. There are 3 different P's. Look at them carefully. They are not the same. Little p is momentum. Capital P is pressure. And for me, script P is going to be power. So watch out for the 3 P's. It turns out force and pressure are related. So perhaps you know from Physics 1, pressure is force over area. And so if you look over here, notice the area drops out between these two. So if you're talking about the force, when something absorbs light, you get this. If it reflects it, it's twice as strong because it not only has to stop it from moving, it has to bounce it off and reflect it the other way. So just be aware of these radiation pressure versus force. Okay, so a little chapter 14 throwback there. All right, so we're ready to go into problems. Before we do that, any questions? I'm ready to start doing some problems. Let's do it. Whoops. Let's start easy. Okay. You could do a quick search for this sometime on your own. It's slightly interesting to see some of these pictures, but I want to point out the following: low energy, low frequency, long wavelength. Remember that for the rest of your life. I'm serious. This is something you should just know as a scientist in general. Low energy, low frequency means long wavelength. Okay. High energy, high frequency, short wavelength. Now, this is how I remember it. UV can give you skin cancer. Clearly, that's high energy, right? And then I remember this, maybe this helps you remember. I just sort of have 3 wavelengths approximately memorized. These are not perfect. There's many different colors of green. For example, 535 or 542.3. There's many different colors of green. These are only approximate. But notice the closer you get to UV, right? Blue light is close to UV. That's around 480 or something. UVs are like 420. If that helps you remember, maybe that will help you. And again, we're talking nanometers. So short wavelengths, X-rays, UVs cause cancer. They have high energy. Okay. So that's how I remember it. Now, frequency here is, again, how frequently it's wiggling up and down. So a red wavelength would be long like this, or radio or infrared. These are the kind of wavelengths, they're so long, they can bend around your entire house, right? You can get radio waves, like your radio will work if you're inside your house. So clearly, whereas, or how about this? Think about a sunset, all right? When you see a sunset, what color is a sunset? Usually, estimate.
Red, orange.
Red. Long wavelengths can get through lots of atmosphere. So at sunset, this will help you remember it. At sunset, the sunlight has to get through so much atmosphere. The really short wavelengths, like blue, they are more likely to bump into molecules compared to those long wavelengths, and so they get scattered away. So that's why the sunsets are going to be red. Yeah. All right. More, but yeah, if that helps you remember, red is a long wavelength because it can get through all the atmosphere at sunset or sunrise. All right. Maybe that helps you remember that. Okay. 33.1. I think you could figure that out. All right. Let's try 33.2. Okay. So everybody, let's take a look at 33.2. You have an LC oscillator, and we're going to use an LC oscillator to produce electromagnetic waves or to receive them. Okay. A good transmitter is a good receiver. So LC oscillator circuits will cause charges to oscillate. That means you're going to give off radiation. Something's fallen off there. I'm just going to write down the specs and we'll get to it. And if you want to just work through all these chapter 33 problems up to whatever I said, just start going nuts and you don't have to listen to me until I say, hey, listen up to this. So 33.2 L equals 3.00 microhenries. C is equal to 175 picofarads. And then we want E gamma, the photon energy. And we want it in joules and EV.
And just to double check here before
Yep.
this,
Yep.
you said that the questions from 32 and 33 on the test, there'd be one from each, and that they would basically be a question from the workbook.
It would be
and
very
that on the-
similar. Like,
and
for
on the
example,
oral
if I threw
exam-
this one in there, it would be, what if it was 2 microhenries? Or what if I change it to 2 millihenries and 17.5 nanofarads? So
Gotcha.
that's a way I might mix up 33.2 if I put it on the test. You know what I'm saying?
Yeah, and then
So
and then you
very
said
similar.
none of these will show up on the oral, correct?
I think I said that. Let me make sure. Let me confirm. Did I have that written down somewhere? Sorry. Where is that? I better not screen share the oral exams. Let me confirm. I
Oh, you
think
don't
that's
wanna-
right.
You don't want to do that? You sure?
Yeah, right. I'm sure you would love it. It's all right. People would still fail it. All right. So we'll see. Yeah, because it's probably
right.
too cryptic for you to understand. It's like my weird cryptic shorthand. What was that? What is this? Fall 20? Come on. Test versions. Final exam helper, maybe? Okay. Just checking some numbers, because this is what, chapter 32 and 33, right? I think you're right. I just want to confirm. Yeah, I don't see any 32 or 33 in the problems that I have listed for oral exams.
Sweet. Thank you.
Got it? But it
Yep.
will be for sure on your final exam.
On the final. Yep.
Yeah, in
Thank you.
some question you have to write. Thank you for checking that. Okay.
Looking very similar to the ones from the workbook, though, right?
Sure, exactly. So the more problems we get done from the chapter 33 workbook, and then I think you'll just be kind of familiar with it. And if you want, you could literally have that workbook problem open and compare it. Obviously, if you've actually done the problem, you'll understand the solution a lot better. So Eston, the color something looks depends. That's covered in Physics 162. Haha. All right. So I'll cheat and get out of it that way. But I could talk to you more in office hours after if you want. All right, let's get back to this one. Okay, so let's take a look at this. There we go. Sorry about that. All right, so in this case, what would you do here? How does this relate to an LC oscillator? It's supposed to get energy. Any equation, anybody. Let's get this rolling.
You could use the equation to find omega using 1 over square root LC, and then convert that to linear frequency.
And then what?
And then you could use that in the equation to find the energy by just saying E equals Planck's constant times the frequency.
Perfect. That's a good way to do it. Now, if you're in chemistry, this is one of the rare times I like to actually talk about chemistry. So in chemistry, what is the symbol for frequency? Tell me, somebody that's a chemist.
Jaden, I think you're the only one in this class.
Come on, Jay, no pressure.
Lambda.
No, that's wavelength.
Is it K?
No, it's nu.
No. Okay.
Now, the reason this is important is because when a chemist asks you what's new, you say E over H. So bad. Or you could say, hey, what's new? Whoops. C over lambda. Take that to your grave. Okay. Anyways, if that helps you remember this, what's new? E over H. Okay, maybe my attempt to teach people physics through bad chemistry humor is failing. But the idea is, I think this walks you through how to do that problem. Now, you better be careful. You better actually take the time to punch these in, just so that you get used to dealing with the calculator with these scientific notation, okay? I'm not trying to lie to you here. It's just, if you haven't been doing the problems with scientific notation in a while, this chapter will get you back up to speed on that, okay? So make sure you actually punch them in and make sure you know how to make your calculator work so that on exam day, you're not sitting there dinking around with that. All right, so that said, pretty easy, right? And then what if you have to convert to EV? Well, I know that this is a good thing to remember. 1.6 is 1 EV. Look at this conversion. If I underline something here, you'll see it. E times 1 volt is this number, right? E times 1 volt, that's what an EV is. It's the charge magnitude of an electron times a volt. Got it? So
Sadly, I saw 1.602 times 10 to the negative 19. I was like, I swear I've seen that number before. It just
yeah.
didn't click.
Now, I know this is going to seem stupid, but this is what I do when I do these. I have screwed up many conversions in my life. Okay, so have you. Now, here's what I remember. EVs are tiny. Joules are big. I know that seems stupid, but that will check that you didn't accidentally write a positive right there. You know what I'm saying? So remember that EVs are tiny. An EV is the energy of a single photon, usually somewhere in that range. Okay, some are 2 EVs, some are a half an EV, but yeah, it's not uncommon to have a single photon. So this is like the energy of a single photon. It's tiny. Okay, EVs are tiny, joules are big. The negative has to go on the big side so that this big thing times a large negative number equals the tiny thing. All right, I'm only saying it because I've screwed it up hundreds of times. Maybe dozens, whatever. All right. So there's how you do that. And then you could look it up on the web and see what type of wave it is. All right, great. Now, this is a fun one you could do at home. If you have a microwave, well, let me rephrase. This is a fun one someone else could do at their home that wasn't worried about safety issues. Okay. You are not, I'm assuming you are not going to do this at home. Normally we would do this in class. This, if you look inside the door of your microwave, you will see this is its operating frequency. Most of them operate at this frequency. Okay. So what you could do is figure out the wavelength of radiation produced by that. If you wanted to, you could probably stick in some pieces of metal that are approximately that size, and they will react very strongly. Do not do that at home. Only a dumb physics instructor would do that in front of their entire class, but you should not do that at home. You could cause some serious problems, so please don't. That said, if you put 2 grapes in your microwave and do this, well, let's just do it like this. This is a fun one. Have you guys seen the 2 grapes? If not, I'm going to tell you anyways. This is a really fun one. Take a grape and then cut it so it's almost all the way apart. The skin, leave a tiny bridge of skin. These are supposed to be the 2 halves of the grape. And very gently place it in there like this so that there's this tiny bit of skin and a tiny little air gap right there, and hit it for 13 seconds. Okay. Turn off the lights and don't huff the ozone afterwards. Okay. But if you, this is a very similar effect. This is what I used to do in college. I would go around to people's parties at the, and instead of drinking beer, I didn't drink when I was in college. Only when I started at Hancock. Correlation. But I would just microwave grapes and blow up helium balloons everywhere. That's what I would used to do. Simple pleasures. Okay. Oh, there was a chat there. Yeah, so obviously there are serious risks with this. I'm kind of making light of this, but do not underestimate this. Like if you put a CD in the microwave, it will just start sparking like crazy, and you will get a lot of ozone, and that ozone is actually bad for you to breathe. So now we could talk about the dosage and this and that. So yeah. Yeah. All right. So okay, this looks like some weird thing. It says memorize this. Okay, and I guess what we could say is since we can't do this in class, it's very difficult for me to tell you all this. So I guess what I'm saying is that's not on the test. But I would say this. There's a small bit of information I want you to know just for your general knowledge. There's a couple of different ways we can create antennas, and you may have seen them in the real world. Very common model of an antenna is two metal rods that are connected by essentially a function generator like this. So the idea is you connect one of these to the red and one of them to the black. Now, obviously, the function is going to oscillate. And as it does this, electrons will be driven back and forth, up and down the rod. That creates an accelerating charge, which transmits energy. The other possibility is a loop, right? You could literally take a loop of wire and put a function generator on it, and current is going to accelerate this way, then that way, then this way, then that way. And so these are the two most common types of antenna, rod antenna and loop antenna. And it turns out this, you probably know this already, but maybe not. Something that makes a good antenna is a good transmitter and a good receiver. However, the patterns at which they radiate energy are very different. So this loop antenna tends to be more directional. This one sends out information in these giant lobes, but all the way around this way and that way. And so if you look at car antennas, right, imagine you have the antenna on your car. Usually it's some sort of rod sticking straight up, right? And here's your car, whatever, there's your bumper, there's your tire, etc. Well, we also know that the power stations where these radio stations come from, there's also a giant rod. And so notice the rods are oriented the same way. And when we're in lecture, I usually show people the differences. What happens is if you put the rod sideways, it sends all the information out into space and not to your car. So this is why we see a lot of antennas that are vertically oriented, because in this case, very little energy goes this way. Almost all of the energy goes out between these two angles here. And so this is a very good transmitter for the Earth. You're sending information out parallel to the Earth's surface. You waste a little bit into the ground, a little bit into the sky, but very little into outer space. Loop antennas can be very directional. Antenna theory is very complicated. If you're an electrical engineer, especially one that's dealing with signal transfer, you'll need to learn about that in a later course. It is no joke. That's enough on antennas. All right, so let's cross out 33.4 now. And that was, we kind of looked at this last time. There's some neat patterns you could see. I'm going to leave 33.5 for you to do at home. It's simple. We're given the intensity of a light wave. You've got some information here. Notice these crazy units. So you have to get used to dealing with prefixes and units and manipulate the equations. All right. Let me get this off of here really quick. I think I missed one. Nope, I didn't. I really like 33.6, so make sure you do a good job on that one. Okay. Let's try it. Let's just check here. Let's do a quick concept check. 33.7. You have red, green, and blue light waves traveling through empty space. Okay. Which one's the fastest?
Would it be blue?
Okay. It's not blue. What's Lul? Maybe I don't know what that is. Oh, my bad. Sorry. Okay, so Claudia had a good guess. I think that was Claudia. She said she thought blue. It's not red.
It's green. I got it. I got it.
It's not green.
What?
Which one is it?
They all go at the same speed?
Light travels at the speed of light.
Dang.
It doesn't travel at the speed of red light or green light or blue light. Now we got to be careful. I was trying to trick you, and the goal here is this. Remember, there's a difference between V, which is wave speed, and F, which is the frequency at which it wiggles up and down. Blue is going to wiggle the fastest, so blue has the highest F. But remember, this is what's tricky. Okay, so blue is going to look, let's do it like this. So there's a blue wave versus a red wave. And so these two waves, I tried to draw them so they have approximately the same amplitude. It's maybe not perfect, but it's close. They're approximately the same amplitude. So that's the amplitude. That would relate to E max or B max, the maximum electric. Oh, I should be careful. This is 2 times the amplitude, right? Because I did the whole thing. So this would be 2 times the amplitude. Now this right here, right there to about right there, is the wavelength of the red, much longer. All right. And then as a result, the frequency of the red is given by C over lambda red. Up here, this would be lambda purple. And we see the frequency of the purple is C over lambda purple. The idea is they both have the same speed, but they do have different frequencies. Just trying to emphasize the subtle wording there you got to look for. All right, so sorry if I tried to trick you. I'm just trying to remind you that now, so you're like, oh shit, I better watch out for this. That was all that was for.
So, quick concept question about
Yep.
that. So, is the wiggle also part of the speed? So it's velocity wiggling up and down. So, like, if you were to send one, if you were to shoot them both off in the same direction, would one get there at a different time because it is wiggling more?
No.
So
It would wiggle more on the way there.
right, it would wiggle more, but it's I don't know how to explain it. I guess because there's a horizontal velocity that they're both traveling exactly the same.
Correct.
But one has a different vertical and vertical velocity. Do you see what I'm saying?
Okay, so yes, that you could argue that the rate at which the electric field changes for the blue is more rapid. So the blue or the purple waves will oscillate more rapidly in the planes perpendicular to the motion. However, they both bring energy from the sun to the earth at the same rate.
Gotcha.
Now, where this gets tricky is if they go through a piece of glass or through water or through air. That's very different. If things go through air, red actually travels, a little bit slower, and blue travels a little bit faster or something like that. We'd have to look at the indices of refraction. I'd have to go look them up. But right, you know how when light travels through a raindrop, it will disperse into different colors? The reason it disperses is because the speeds of the colors are different in glass. They're different in air. They're different in medium. Okay. However, that's the subject of the next class, so I don't want to spend a lot of time on it. And I may have flipped it. I can't remember. Let's just worry about that in 162 right now. I want to focus on right now for us in this class. Our waves are traveling through a vacuum. Okay. Good on that, Nick?
Yep.
So in glass, what I'm saying might not be true anymore. We'll worry about that in 162. All right. Okay. Let's see. This is pretty cool. This is just another practice problem where I give you a wavelength. This is really easy stuff, right? So not too crazy. Oh, here we go. Let's try this one. 33.9. Let's work together, people. In this case, let's say you have 2 plane electromagnetic waves, case 1 and case 2. Let's start with case 1. In this case, which way is that wave propagating? Do you remember how we tell which way the energy is traveling?
It was B cross E, I think.
Close.
E cross B then.
Very good.
All right.
E goes to B, goes to direction the wave travels. Again, E goes to B, goes to, all right, so which way is that? Let's see, I think you're right, Wilfredo. Negative K hat for case 1. Got it. Let's try case 2, everybody. Everybody try it again. Just make sure you got that. Oh boy. Oh man, I'm gonna have to think now. Okay, so first I got to figure out which way J hat points. So I better write my wheel of pain because I'm going to get lost. I goes to J, goes to K, goes to there. So in this case, I goes to K, goes to what? Negative J. So that means negative J is what? Out of the page? So that means positive. So positive J is into the page. Did I do that right, everybody? Double check by just checking I goes to J goes to K. I goes to J. Yes. So that was correct for J hat. Now E goes to B goes to what? Negative K hat? Nice, Claudia. I think you got it. So you can see it gets a little tricky because you got to look both at the coordinate system and the values of E and B. Okay. All right. All right. So that's a good practice problem for you. Hey, look at this problem, 33.10. Most of this you could do, but just tell me, let's just focus on this for right now. Which direction is this wave propagating? Take a second to think it through. You could answer in the chat or unmute. So which way is the energy traveling when I give you this type of information? Let me ask another way. Which way is it not propagating? Which way can you tell immediately that it's not propagating?
Not in the J hat.
It's not in the J hat because the electric field is not going to oscillate in the same direction as the energy travels. That's what Nick and I were just talking about, right? We said the electric field oscillates perpendicular to the direction the wave travels. It's not I hat, so that leaves...
Why isn't it I hat?
Where are you supposed to look? Right here. The thing inside the sine function tells you which way it travels. If it's kx minus omega t, that was I hat, remember?
It goes negative k.
Yeah, and so if this was kx plus omega t, it would have been negative I hat. So Tom, what did you say it was?
Negative k.
And that's not right. It's in the positive k hat. So
Is that because of the minus sign?
The minus sign means plus because physics is tricky, right? So the idea is the z is what tells you it's in the k hat. The minus is what tells you it's a positive. The standard way of writing waves is always kx minus omega t, or actually in general, wave numbers are three-dimensional vectors. And so it would be k vector dot r vector minus omega t. And so we see that if you have a wave written in this form, it's traveling in the r hat direction in general. So basically, if you have the minus sign, that means we're going in that direction right there. Is that clear? Or Probably
A
not.
quick question.
Yeah.
K is the value we determine 2 pi over lambda, right?
That's right. That's called
Okay,
the
so-
wave number.
Then the z, what value would z represent in this case?
Z is anything in space. So if I could, let me go back to this one. Even though I'm sorry, this one's in the XZ plane, so this is a slightly different wave. But the idea here is this. At some point in time, let's say this is Y value, right? What we see is at any one value of Y, the B field and the electric field are oscillating up and down. So let me go to the whiteboard. This is how wave equations work, all right? So this is a traveling wave equation. Let's say we have this equation here, E max, and I'm going to actually use the one that we have in our problem. So let me bring that back up. This one? Okay. So I'm just getting it down. So it looks like we need to look at this one. I'm just going to say number T. This is in the J hat, I think. Okay. So the equation that was written in that book took this form. Now, I just want to pretend, I want to look at this in a couple of different ways. Let's say, what if T equals 0? That would be like taking a snapshot of the wave at one instant in time. Well, if I set T equal to 0, this term drops out. And then it would be E max is equal to 2.22 volts per meter. I'm just going to say E max because I'm tired of writing that. Okay. Whoops. Sorry. This is E as a function of X and T or whatever. Let's just say E. Okay, so if T was equal to 0, you get a sine wave. So what does this mean? If you go out some distance from the origin, that will tell you what the electric field is at that spot at this time. Now, if you go to a slightly larger time, oops. The idea is after a short period of time, that's going to change. It basically introduces a phase shift, if you will. But what we're seeing is the sine wave will shift. So at the same position in space, the electric field will be different at some later point in time. So now the same thing is also true if you set Z equal to 0 and then look at the wave over time. So so the idea here is if you take time and set it to a discrete value, at any one instant in time, you could plug in that number and see the wave throughout space. If you look at, if you set Z to some number, you could look at the wave as it travels throughout time. So at one particular location, you could also see how the electric field is oscillating at that one spot over time. Is this helping at all, Nick, or is this making it worse?
No, it's helping. I don't have a full grasp on it yet, but it's helping.
So if you really wanted to get a feel for it, one of the things you could do is, well, number one is take Physics 162 next semester. That's the easiest way to learn it. The other one is you could make a plot in Excel and punch in some numbers for this. And then the idea here is, let me see if I've got something that might help just a little bit. Watch this. Let me see if I've got an old thing that might help. Whoa, let's get rid of that. Almost did show you the final exams. Whew. All right. Oh, God. Just looking at that makes me want to puke. Let's see. Where were we? Which one is it? Let's try this one. So let's see, waves. So you're going to do a lot more with waves and phase angles in there, probably. I know what to look for. So that's oscillations. Waves. All right. So here's the idea. If you look at this, this is supposed to be showing these images. And I'm going to just kind of, can I make this a little bit smaller so you can see more? The idea is, notice what the axes are. This is a position and this is a position. So this would be like the height of a water wave as it's traveling across the lake. This is at t equals 0. This would be at 1 second. Notice it's moved to the right a little bit and it keeps moving, right? And so the idea is, as time goes on, the wave changes location.
Got it. That makes sense now.
Now, think about this. What if I just look at the height right here? See how the height is changing? And so right here, it might be right there. So you could also look at, if you picked a set value for X, you could actually see it changing with time. So the height of one piece of water just keeps changing up and down over and over and over again. However, the wave travels to the right. And so there's these two complex patterns. There's no simpler way to say it than it's an oscillation in space and time. So sometimes people will actually write this here like I was starting to do, and I got lazy. Instead of just saying it's an electric field as a function of time, they'll say it's an electric field as a function of, in this case, it would depend on both z and time. Good enough?
Yep.
It's weird, right? Now, if you make your own spreadsheet, you could do that. And I think, did I have that there? Oh, all right. Yeah, that's not what I want to go into. All right, so yeah, let's leave it at that for now. If we have time, I'll show you more. I've got some simulations. Okay, so let's take a look. I like what Trey says. Think of it like a weather map. It matters where and when you are looking at it. Sure, I agree with that totally. Except for Lompoc, it's just always fog, right? Oh, burn.
Yeah, he's
Only
not
in the
even lying.
mornings.
That's like the truth.
Only in the mornings. My bad. My bad. Only when there's supposed to be a launch. Yeah, right? Hmm. All right.
Exactly.
All right.
Except this Saturday was perfect. Oh my gosh.
Oh, all right. I'm looking at the time. I know you guys are tired. I'm just going to keep plowing through this because I think we're very close to being done. So I'm not giving you a break. Sorry. All right. I don't normally do that to you, but I think we've only got like 2 or 3 more problems here. Let me check. Actually, maybe we should take a short break just to let you pee. Where's those questions? No, not that. This one. We're only supposed to go up to 16. We're going to make it. Let's take a quick 5-minute break. All right. I promise not to be late. 5 minutes. Okay. 5 minutes. And then we'll pick up here because these are significantly different. So 11 through 16 is a little bit different. Okay. Take a quick 5-minute break, recharge your battery, stretch, etc. Come right back. All right. 5 minutes. 6:10. Eston, did you get that all figured out, or are you even here right now? You were asking something about the sun. Probably on break.
Hey, Jorstad.
Yo, what's up?
Yo, so about the sun, right?
Mm-hmm.
So I'm thinking if the whole atmosphere thing makes the sunset red,
Mm.
then wouldn't we expect to see like all wavelengths of light, right?
At high noon.
Or if we're just in space, if there's no atmosphere,
Mm-hmm. Yeah.
if we
Yeah.
could look right at this, so would the sun be white then?
Yeah.
Okay, cool. That's all I need to know. It was a heated debate in the Discord, and many lives were lost.
Oh. Yeah. Well, so the idea is, I tell you what, we'll look at it right afterwards. All right. But
Alrighty.
the sun, think about the human eye, right? Our eye is optimized to see red, green, and blue. Clearly, the sun puts out wavelengths right at that, which is white when you add them all together. And it depends on the surface temperature of the sun. How hot do you think the surface of the sun is?
Pretty hot.
Yeah, give me a number.
Oh, I have no idea. Like a thousand Kelvin. Is that hot? I don't know.
Oh, that's not that hot.
2 billion Kelvin. How about that?
That's
pretty
like
hot.
this. That's like the core of the sun.
Yeah, see, so I got it.
It's about 5-6 K, kilokelvin. So yeah. So it's about 6,000 Kelvin. All right. So it turns out it's not that hot. However, the internal temperature where fusion occurs is several million, right? So anyways, yeah, I think, did you say billion or million?
Yo, let's just say I said million.
Let's hear you said million, because that's about right. All right. So very good. Very good. All right. That said, we could talk more about fusion and all that later.
Sounds good, dude. Thanks.
Yep. And I've got an animation I could show you that. So that said, let's talk about this problem here. Now, I know a little bit about lasers. All right. I used to work with lasers. So this is a very common wavelength of what color?
I want to say green.
Green. This is a green laser. 532 is a famous green. What's a famous red laser? Heaney. It's kind of a red orange at 633. So those are two extremely common lasers. Okay, 532 at 633 nanometers. All right. How do I find the average intensity of the beam? So let's read this. It's got 10 milliwatts. This is what, a strong or a weak laser? What do you think? It's only milliwatts. What do you guys think?
That seems like a relatively strong laser.
It is. anything over 5 milliwatts can cause permanent blindness. If we use that as our standard, this thing is cooking. All right. 10 milliwatts will burn you. Yeah. 10 watt laser will burn you severely instantly. I have been burned by a 10-watt laser. It does not feel good. It put a hole through my shirt and just burned me. So don't stick your hand in high-powered laser beams. Okay, next. How do we get the average intensity? Any beer drinkers out there that have a suggestion what equation we might use?
IPA.
IPA intensity equals what? Finish it out for me.
P over A.
P over A. Good. So it's watts per meter squared. All right. So let's just check. We've got the power. We've got, it says the power is distributed uniformly over this cross section. That's not exactly true. It's usually a Gaussian wave profile, but this is beginning physics. Let's just keep it easy. We know the area. We know the power. I've got the intensity. Now take a look. Is this going to be intense or not? Well, I've got milliwatts, but then it's over millimeters squared. So one of these millis will cancel there and I'll get kilowatt per meter squared. That's a lot. That's literally, that's intense, bro. That's intense. Whoa, that's so intense. And in fact, my children are sitting outside in a tent. That's intense. It's very different, but yeah, okay. Next, if you want, I'm losing it. I don't care. Okay, if you want, you could compare this to the surface of the sun, and maybe just to save some, you are not going to miss these jokes. I guarantee you that. That is a certainty. But yeah, these. Let's see. I just wanted to show you. Oh, I should actually clear this crap. Let's skip to some of the fun. Let's compare this pretty intense laser beam to the sun. Okay, so you could imagine this is the energy emitted by the sun over that giant radius. Okay, all right. So let's go look somewhere. There's a solution, I think. What question was this? 11? Oh, let me mention something. Make sure you do these problems. People have trouble checking the units. So I did a lot of work to help you figure this out. Look at how crazy these are. So make sure you do these problems just to get used to the units. All right, that said, what problem are we on? 11, I think. Oh, there's the story of pointing, if you care. I'm not really into talking about the stories of people, but nice try, Nate Dogg. The 555 goes in the address and the 420 goes later. Geez, come on, man. You're so outdated. All right, whatever. Let's keep going. Oh my gosh, so boring. Here we go. Green with just a kiss of blue. All right. All right. Ooh, look at this. There you go. That's really why I talk about 555 all the time. The human eye is most sensitive to that wavelength. I think that's actually true, but I don't believe myself because I put 555 on everything. So you better double check that. That said, here's this laser beam, 33, about 353 watts per meter squared. So close to a kilowatt per meter squared. The sun uses a spherical area. This is a very common thing. I know we're kind of tired and I'm starting to get a little loopy. Notice this something right here. This is the most common mistake students make with these intensity problems. If you have a spherical area, you need to use the surface area of a sphere. If you have a circular area, you need to use the circular area. So watch for that in all of these questions. Please, please, please. I know we're tired and goofing off, but okay, so it looks like the sun is just slightly more intense than this laser beam. Megawatts per meter squared. So yeah, that's a lot bigger. All right, let's go back over here. Okay, and so once you know the intensity, don't overthink it. It's basically practicing where are the equations you need And so if I could, I'm going to go to this one. Sorry. It's kind of just getting used to these equations and playing with them a little bit. The intensity is on the back or that one key page. And notice somewhere in there, the intensity relates to the electric field max and the magnetic field max. And it's simply plug and chug and get used to the prefixes. So this chapter is all about keeping track of your tendidas, your prefixes, your constants, and that's it. Okay, it's just attention to detail when plugging in numbers, an important skill for any engineer, scientist, what have you, computer scientist too. All right. So that said, these two things are basically plug and chug. Similarly, let's see, the wave number and angular frequency. Well, let's think. So this one comes from the I average equals E squared over some stuff, blah, 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 blah. Where does this equation come from? How do I get the wave number? Remind me.
Pi over lambda.
Yeah, nice. So this is K equals 2 pi over lambda. And then once you get that, if you know the wavelength, you've got the K vector. You could also get omega. How do you get omega, the angular frequency?
Uh, 2 pi f,
How do you get F?
inverse of wavelength.
Not quite. The chemist says, what's new? Remember, F is like new. What's new?
E over h.
E over H. That's true.
Oh,
You
wait,
could do it that way. Or also this way. C equals F lambda. So it's also C over lambda. What's new? E over H. What's new? C over lambda. So yeah, you had the right. It's not exactly 1 over lambda. It's the units don't work, right? F is C over lambda. Got it? But again, it's just kind of, so you could actually do these questions on the final exam without doing this chapter, but you'll probably be so slow, it'll cost you time on other questions. So it's just basically, I'm giving you some work to do. These things come up in many branches of science, so it's important that you get some exposure to them. All right. And then lastly, write down these electric field and magnetic field as functions of space and time. It tells you which way it's traveling. I'm going to let you try that one at home. Okay. The rest of it. But so we've kind of sketched it out, parts of this one. So this is a good one. It's the same information that we've already done. And then I just rephrased it in a different way. So you can see all these questions are the same. By the time you do 3 or 4 of them, you'll be like, I got this. All right. This is slightly different. So I want to kind of walk you through this one. 33.12. We're told the power and the wavelength. Okay. This one usually throws people for a loop. We're told the power is what, 10 milliwatts or 5? Okay, so 5 milliwatts, decent. That's the start of class 3 or whatever. Okay, and we're told lambda equals 632.8 nanometers, a nice red-orange helium neon laser. Okay. And we're trying to get the energy of a single photon. I'm going to need some help here, people. I want the energy of a single photon. Any ideas, any guesses how we should approach this? I know you could look at the solutions, but at first this seems like, what? Oh, go ahead.
Well, energy is watts per second, right?
You're on the right track. Unit analysis is the right approach. Good. So wait, what's this unit?
What?
Watt. What is 1 watt equal to? Start that way. What's the general definition of power?
Joule per second.
Yeah, okay. How about work over time? Or DEDT is maybe something you've seen it. Now, here we got to be careful. This is energy, the energy DT, not the electric field. So I'm going to write it's work over time, which is change in energy over change in time. All right. So the units of that are joules per second, right? So you're like, I've got watts. That tells me how many joules per second. All right, so try to give me an equation that relates all this crap to what we're looking for. How is this energy going to relate to that power? You've got this beam coming, right? So all of these are coming at you, all right? And we know the power related to all these, right? So we know the power that is delivered. How does that relate to the energy of each one and the number per second?
I have a quick question.
Uh-huh.
Why couldn't you just use the wavelength to find
You could.
the
You
energy?
could. I was answering part B. I didn't realize it.
Oh, got it.
J is correct. This would get you part A, right? Sorry, I was jumping ahead. So J is correct. We could just use E equals HC over lambda. We know lambda. HC is 1240 EV nanometers. Done. Sorry about that. J is correct. We didn't need to do this discussion yet. I'm looking at this one, the number of photons per second. Sorry about that. My bad. My bad. Jumped ahead. So how do we get the number of photons per second now? So we know the energy, we know the power. How does that relate to the number per second? Do the units.
Is power equal to energy times frequency?
Okay, but not frequency. It's number per second. Isn't that the same units as frequency? It's 1 over seconds. And now we know this, we know this. I've got the number per second. That's something that's a little bit weird. So I just wanted to walk you through that one step. Jay, you were pretty much on it. So the frequency at which the photons pass this surface area would be the number per second. Is that good?
Yeah, that makes sense.
Yeah. And so once you know that, the rest of this problem is a piece of cake. But I just wanted to make sure you guys understood that under a kind of slightly weird connection there. Comes from the units. So let's go back and look at this one here. Momentum of a single photon. Before we get, what would you do if this showed up on test day, people? If I asked you for the momentum of a single photon, just describe the process you would follow. What's something you would try?
H over lambda.
Yeah, I was going to say, look at the back of the book and read the equation sheet. That's what I would do. So, yeah, but Tom already did that. So, yeah, just showing you, I'm not trying to lie to you here. I'm just thinking, okay, there's a momentum frequency right there, or a momentum photon, its energy there over C, which notice that if we know this is the energy, there's the momentum, piece of cake. All right. Nothing fancy. It's just, can you read? I'd grab an equation, use math. Should be easy stuff. All right. Okay, and we already talked about kind of a red-orange. All right. Let's talk about this one. An astronaut in space holds a battery-powered 10-watt laser. The astronaut is motionless relative to her spaceship and has run out of thrust or fuel. She is untethered and cannot simply pull her way back to the ship. She is 10 meters from the ship. You could bet she is freaking out right now. Okay, how could she use the laser beam to get back to her ship? Describe the physics of it conceptually for me. I'll draw it up. Let's say the astronaut is right here. Let's say the spaceship is right here. Spaceship.
You could point the thrust or the laser away from.
Okay,
her.
so here's the laser. She shines the laser away. Why does that do something for her?
Because it has a force and it'll be equal and opposite pushing her back.
Okay. When you talk about that, you're talking about equal and opposite force. That makes me think about what other physics concept? That was the last part of the previous problem or close to it.
The momentum?
Momentum. Can you describe to me, let's say right now she's at rest. What's the momentum of the system?
0.
0 relative to this spaceship and her. So when she turns this on, let's say she turns on and one photon goes this way. That photon has some momentum. Gamma is, again, the symbol for a photon. So I send some momentum that way. What's going to happen to her? Which way will she move?
Opposite.
Yeah. Now here is the dilemma. If she does this, it's going to take a lot of photons because each of these momenta are extremely small, right? In theory, though, she could turn on the laser beam, point it that way, and over time, she'll slowly start speeding up and go back to the spaceship. Now, to be honest, she might be gravitationally attracted to the spaceship more rapidly than this. But yeah, you get the idea. The other thing she could do is just take the laser and throw it. If she throws the laser beam away from her, she picks up significantly more speed. However, she only gets one shot. And then she's either dead or might make it. So, moral of the story, don't get lost in space.
Quick question.
Yeah.
Okay. Does it matter how fast she throws it? I
Yeah.
don't think it does
The
it?
faster you throw the faster you throw the laser, the more momentum you gave to it, the more recoil you have.
Okay.
Now, when you shine the laser like this, when you just shine it, it's a slow building, right? Because each little photon you shine out there adds a little bit to your momentum. It's more like the well, let's just leave it like that. It's a slow building acceleration. Got it? So instead of one giant impulse, it's slowly building. Good enough on that, Nick?
Yep.
Oh, yeah. So the moral of the story is never take one of Ryan's ships. Never trust it. I mean, would you trust somebody taught by me? I wouldn't. Come on.
You mean duct tape's not like the best way to fix a spaceship?
No, it's Gorilla Tape. Come on. Where you
Oh,
been?
shoot. My bad.
Yeah. All right. Let's get back to it. All right. So, yeah. Basically, don't get lost in space. All right. Now, here's an interesting one. Explain the physics of a solar sail. All right. So let's walk through. I don't know. Somebody try it, and then I'll show the solution on the screen. What do you think? Why does a solar sail work? Forget the question. Just explain how a solar sail works.
The photons produce a force on the sail.
Okay. You have a photon coming in here. It's shiny. It gets reflected. There's a photon coming in. Assuming it doesn't change color when it reflects, it's the same momentum going out. Wait a minute. Does the momentum of the photon change?
Yes.
What do you mean? I don't understand.
It's now going in the opposite direction.
Momentum is technically a vector, right? So notice the change in momentum is equal to 2 times the magnitude of one momenta. And then it's either going to be in the plus or minus I hat, depending which object. So clearly, if the momentum of the photon changes by negative, this one will change by positive. And so literally, you take a small satellite, you unfold a giant sheet of mylar, the light bouncing off it will produce a tiny amount of momentum. Now, keep in mind, out in space, if the sail is big enough, this will actually work. If you look at the math on it, it's slightly interesting. So let's scroll down. I did all the math for you. Oh, there's that one. Okay. Oh, look at this. It says it would take yeah, that's the laser beam math. It's pretty funny. But so the idea here is the momentum change is twice that. All right. And so if you do the math on this one, I kind of walk this out. In general, there would be a force from the radiation and then a force from gravity. So imagine this thing is trying to escape the sun. You're trying to send something to deep space. So you're trying to send it radially away from the sun. Okay. And let's assume it's just literally the piece of foil with negligible other mass. Well, the force due to gravity will be pulling it like this. The force due to the radiation would depend on these factors. And then blah, 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 blah. It walks you through. This gives you an acceleration. So if you walk through this one, look at this. We expect the acceleration of the foil to decrease as it gets farther from the sun. It ends up having a 1/r² dependence because the intensity of light also falls off as you get away, right? The sunlight gets weaker as you get farther out. So this acceleration gets smaller and smaller and smaller. All right. I'll let you do the math on that at home. Let's check one more. I know it's time to go. If you've got to get out of here, feel free to leave. That said, okay, this is a good one to look at and end on. And 33.16 is a good one for, this is optical levitation. It's really cool. If you're curious, you could look up how optical tweezers work. And this relates to using laser beams to grab one end of a DNA molecule. So there's lots of cool applications of this stuff. That said, I got to focus on helping you pass. So I'm going to just do the start of this one. So 33.15. So you know that big Arecibo thing that just got decommissioned because of all the hurricanes? I don't know if you heard about this. That big 100-meter dish down in, where is that? Is that in Puerto Rico? I forget. But basically, it just got destroyed. It's really sad. That said, if we look at how this looks, let me show you something here, right here. I think this sums it up. So light from the sun is, or from a distant star, is actually being transmitted spherically. So the energy is going out in all these directions, and it's traveling perpendicular to these wave fronts. So you could think of these lines that I've drawn as like the crest in the sine wave. Here's the next crest of the sine wave. And because this is going out spherically, we see this energy is spreading out. Now, by the time light from a distant star smacks into our planet, I just want to point out it's effectively hitting a circular cross-section, even though it was spreading out spherically, because over this distance, all that light is essentially traveling the same direction. So when all the light waves are traveling the same direction, once they get close to here, we call it a plane wave. So the equation that we had, this E equals some crap times sine kx minus omega t. This is the equation for a plane wave, one that's traveling in a straight line, and all the photons are traveling in a straight line. Even though the star radiates spherically, by the time it gets to any sort of detector, it's actually a plane wave at the detector for all intents and purposes. And so this is a little bit confusing when you first see it. So notice the intensity at the planet's position is the power of the star divided by 4 pi r squared, because it's spreading out over a spherical area. Now, the power received by a circular dish uses a circular area. And so notice we get this circular area over the spherical area, or this power received relates to the area of your receiving dish versus the area of the wavefront. And so there's a little bit of confusion here sometimes between the pi's and the 4's, but notice this factor of 4 does not drop out. Okay. Same thing is true if you think about sound waves. Sound waves travel out in spheres, but when it hits your eardrum is a tiny little plane. And so it's going to hit a circular area. So the intensity of a sound wave spreads out spherically, but the intensity, the power received by your eardrum relates to a circular area. So I'm going to leave it at that. All right. Oh, the quiz list. All right. Yay. All right. So I think that's pretty good. Let's go ahead and stop the live stream. And maybe I'll say one last thing. Don't forget to do all the problems up to, what was it, 16? I think that's what I asked you to do. So I think you're supposed to do all of them up to here. And if you look in the workbook, it says, if you need more practice, try these, but those are not the ones that are going to be on the test. So these are not the ones that are going to be on the test. It would come from those first ones. So hopefully you only have a few more problems to work on, and maybe a few parts. There's a few in there that you got to work a little bit on. Now I'll stop the live stream.